Welcome to this video on the Newton-Cotes integration method, where at the end of this video you will be able to calculate integrals using Simpsons methods. So as a reminder, what we're trying to do is we're trying to calculate the area underneath a curve by integrating a function f of x from a to b. And for Simpsons methods, we are now going to use second-order polynomials to approximate the integrand f of x. So shown here is an example of a function f of x, and we're trying to approximate the area underneath this curve by the area underneath a second-order polynomial shown here in blue. And in order to define a second-order polynomial, we need, of course, 3 points. And what are those 3 points? Well, we have two that are kind of obvious. Those are the two endpoints of the integration at a and b. But what are we going to use for the third point to define the second-order polynomial? Well, it kind of makes sense to use a point in the middle of the integral. So that would be at a plus b over 2. So those are our 3 points that now define the second-order polynomial that goes through those 3 function values: x1 equal to a, x2 equal to a plus b over 2, and x3 equal to b. How are we going to find that polynomial? Well, we could use, for example, a Lagrange form. So this is the Lagrange polynomial form of the second-order polynomial that goes through these 3 points. And now all we have to do is to integrate this polynomial analytically. And if we use h as the constant spacing between neighboring points, which is guaranteed in this case because the x2 point is in the middle of the integral, we will find that the integral, the approximation to the area underneath the curve, is the integral of this polynomial. And if we go through all the math steps, we'll find that this is 1/3 times h, the spacing between neighboring points, times the function value at the first point, plus 4 times the function value in the middle, plus the function value at the end of the integral. And you would see this factor 1/3 there. That's the reason for the name, why we call this method Simpsons 1/3 method. Now, we can improve on this by not integrating in one sweep over the entire integral from a to b, but instead using a composite version of this by splitting the integral into subintervals of equal size. And let's say the equal size of these subintervals is equal to h. If we have n of those subintervals, the size h would be b minus a divided by n. So that means here we'll have now n subintervals, and we define, what? We need 3 points to define a second-order polynomial, which means if we look just at the first subinterval, we only have 2 points available. So where do we get our third point? Well, we don't really have to go to the middle of the interval anymore, because we have now additional points available, and the additional point is just from the next interval over. So what we'll have to do is we need 2 adjacent subintervals to give us the 3 points that we need to define the second-order polynomial that we analytically integrate in Simpsons 1/3 method. So this would then be the first subinterval, and this would be the second subinterval that we're using. And we are integrating over those two subintervals combined. So that's the integral from x1 to x3 of f of x dx. Now then, the next pair of subintervals that we're integrating over would be this one from x3 to x4 plus the one from x4 to x5. So we'll have to add the integral from x3 to x5 of f of x dx. And we keep on going, right, over every pair of subintervals until we get to the ith pair. And that would be the integral from xi minus 1 to xi plus 1 of f of x dx. And then we'll keep on going until we hit the last pair of subintervals. And that last pair of subintervals goes from xn minus 1 to xn plus 1 f of x dx. Okay, so now let's write this with a sum, right? Because we're taking the sum of individual integrals. And that would be the sum over the ith interval pair formula. So the integral from xi minus 1 to xi plus 1 f of x dx. Now we have to figure out what is this index I summing over. So we'll look here at the bottom. So we start at x1 and right, so that would mean I would have to be equal to 2 so that this lower bound, which in the formula is xi minus 1, be 1. So I equal to 2 makes the lower bound x2 minus 1, so x1, exactly the lower bound of the first integral here. Next up is x3 as the lower bound of the next integral. So how do we get that if what's the I have to be so that xi minus 1 is equal to x3? Well, that would have to be I is equal to 4. So we go from 2 to 4 and so on, then to 6, and we keep on going. And how far do we have to go? Well, the last integral that we have to sum over starts at xn minus 1. But in the formula we have xi minus 1, so the I would have to be equal to n, so that for the last integral we have x sub n minus 1 as the starting point of the integral. And now we should really double check whether the upper bound is satisfied as well. For the first integral, the upper bound is x3, and in the summation formula the I would be equal to 2. But in the formula the upper bound is xi plus 1, that would make the upper bound x3 for the first integral. Then I becomes 4, the upper bound x5, so that checks out. All the way to the last term, I would be equal to n, so in the formula the upper bound then is xn plus 1, that checks out as well. So then this is Simpsons 1/3 method for the subintervals, right? That we'll now have to use for this integration. So we take Simpsons 1/3 for the integral from xi minus 1 to xi plus 1. So, right, that would give us 1/3 h times f of the first point, that's xi minus 1, plus 4 times the point in the middle, that would be f of xi, plus 1 time the point at the end, which is f of xi plus 1. And now all we have to do is substitute this into the sum formula that we defined before. So it's again the sum from 2 to 4 to 6 to all the way to n of this discrete version of the integral from xi minus 1 to xi plus 1, which is the 1/3 h times f of xi minus 1 plus 4 times f of xi plus f of xi plus 1. Okay, so let's take this formula here. And if we look at this, this means that we have to have 3 function evaluations for every 2 subintervals. Now, if it is very costly to evaluate each function, we would want to have a formula that speeds this up, that minimizes the required function evaluation. And we saw that there's something like this possible for the trapezoidal method. So maybe something like this works for the Simpsons 1/3 method as well. So let me write out this sum. So I'm going to start out with 1/3 h, which is in each one of the summation terms, so I can factor that out. So I have 1/3 h times, let's start with the first set here. I have f of I equal 2, so x 2 minus 1, so that's f1, plus 4 times f2, right, at the second point, plus f at the third point. Okay, so that's everything for I equal to 2. Let's move on to I equal to 4. So I have f at 4 minus 1, so f at 3, plus 4 times f at 5, plus 1 time f, what did I say? Plus 4 times f at 4, plus 1 times f at 5, that way. So then let's move on, right? We go to the 6th and so on and so on. Let's move on to the ith one. So we have f at I minus 1 plus 4 times f at I plus f at I plus 1. And then we'll march on with the sum until we get to the last one. So that would be f at I is equal to n, so f at n minus 1 plus 4 times f at n plus f at, right, the last one here, f at n plus 1. Okay, so now if we look at this, let me copy the 1/3 h over again. And let's go through these terms one by one. We'll see that the first point and the last point's function values, they appear just once in this formula. So let me just write them as is, right? There's nothing much I can do about them. But then let's look at the next terms. There are some function values that get multiplied by 4, right? And those are the values at 2, 4, 6, 8, I, all the way to n. So that would be 4 times the function value, the sum of the function values fi, where I starts at 2, then goes to 4, 6, all the way to n. So 2, 4, 6, all the way to n. So we go by 2's. And then we have some function values that appear twice, which means we can combine them, and that would leave us to 2 times the sum of fi, where I starts at 3, then goes to 5, 7, all the way to n minus 1. So we go again by 2, but we start with the odd points. 3, 5, 7, all the way to n minus 1. Okay, so that's the equivalent, more compact formula, where we actually need to evaluate the function only once at every one of our data points. Now, strictly speaking, this formula is valid only if the subintervals are equally spaced, right? If there's an h that I can pull out, and the number of subintervals is even, because I have to combine always 2 subintervals together. Now, if we have an odd number of subintervals, then what we'll have to do is we have to use the trapezoidal method for the last interval. Okay, and everything before that has to be an even number of subintervals. We can use this formula for Simpsons 1/3 method. Okay, let's do an example for this. So here is the data again for the example. We have x values and the corresponding f values. And we want to evaluate the integral of f of x dx using Simpsons 1/3 method, which I copied over here. So first off is we should figure out how many subintervals do we have to make the determination whether we have an even number or an odd number. So let's just count this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 subintervals. So our n is equal to 10. So therefore we have an even number. So we can directly apply this formula. What's our spacing? H is the distance between adjacent points. So that's always a constant, and that is in this example, h is equal to 1. Okay then, so let's use the formula to approximate the integral. So I of f is approximated by 1/3 times h. So that's 1/3 times 1. That's my 1 here, that is the h. Times, okay, let's look at the formula. I need the first function value, that's f1, that would be this one. And then I'm looking ahead here at the end. I need the last value, that would be fn plus 1. So let's start with the first function value. So that is equal to 0. Okay, so that is the f of 1. Then plus 4 times the sum of, let me just write up here so it becomes apparent what the index is. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? 10 subintervals means 11 data points. And now for this sum that contains the prefactor of 4, we have to take the values at 2, 4, 6, 8, all the way to n, but n was 10, so all the way to here, the 81. So let me write those values here. I can sum them up. So 1 plus 9 plus 25 plus 49 plus 81. Okay, so those are everything that I have to sum up for the prefactor of 4. Then I have plus 2 times the sum of these values at 3, 5, 7 all the way to n minus 1, which is equal to 9. Okay, so let's go purple here. So we have 3, 5, 7, and 9. So let's sum these up. So we have 4 plus 16 plus 36 plus 64. Okay. And then we have at the very end plus fn plus 1. That was my sine one, so plus 100. Color this one in. Okay. And everything gets multiplied by 1/3 times 1. Okay then, so if you plug in the numbers here, you will find that the answer is 333 and 1/3. Okay, so that would be the final answer. One quick way of double checking that everything works out in this formula is to see whether in the table here every single f value is colored just once. So it appears just once in the final formula, and that's the case here. Now the other thing to notice is that in a prior video, when we integrated this data, we talked about that these function values are actually just the square of the x values. Right? So this data here, fi of xi, is just equal to xi squared. And if we do the analytically exact solution for this, for the integral of f of x dx from 0 to 10 is 333 1/3. And you'll notice here, right, that this is the exact analytical solution that we get with our method. So how can that be? Well, it's because Simpsons 1/3 method is derived by assuming that I can approximate the function that I'm integrating by a second order polynomial. And that's exactly what this data is. It's a second order polynomial. So therefore we expect this method, Simpsons 1/3 method, to be exact up to round-off errors. Okay, so what more can we do? That was Simpsons 1/3 method. Now let's go to Simpsons 3/8 method. Again, area underneath the curve. And now instead of using a second order polynomial, let's use a third order polynomial to approximate the integrand. Same type of idea, but in order to define a third order polynomial, we will need 4 points to define this polynomial. And what we're going to do is we're going to use the 2 endpoints of the integral, so a and b. And now we're going to interdisperse 2 additional points into this interval that are equidistant apart from the neighbor. So equally spaced. So the first point then that we place in the middle would be 2/3 a plus 1/3 b. And the second point would be at 1/3 a plus 2/3 b. And now the task is find the third order polynomial that goes through those 4 points. We could use Lagrange polynomials. Then we would have to analytically, right, integrate this, assuming that the spacing is equal between neighboring points. And if we go through these steps, we'll find that this integral would be 3/8 times h plus f at the first point, plus 3 times f at the second point, plus 3 times f at the third point, plus f at the fourth point. And you see the prefactor here is 3/8. That gives the method its name, Simpsons 3/8 method. Now, how about using again n subintervals to improve the method? So we're going to subdivide a to b into n subintervals of equal size h, which makes the size b minus a over n again. But we need 4 points to define the third order polynomial, which means we have to add additional subintervals to our integration to get to those 4 points, which means we have to always integrate over 3 adjacent subintervals. Okay, so that would be those 3 for the first part. So the overall integral would now be the integral from x1 to x4 of f of x dx. And then the next part would be the integral from x4 through x7 of f of x dx. And we would keep on going. Okay, so next up would be, if we look at the ith integral, well, actually here we'll look first at the next group of integrals. That would be x7 through x10. And then finally, we will look at the ith one. So the ith one would be from x, well, actually here xi minus 1 to xi plus 1. But if we go then over to the very last one, we would have x of n minus 2 to x of n plus 1. And now we're going to use Simpsons 3/8 method for each one of these subintegrals, which means that for the very first one, we have 3/8 times h times f1 plus 3f2 plus 3f3 plus f4. Now Simpsons 3/8 for the next one from x4 through x7. So that's another f4 plus 3 times f5 plus 3 times f6. Then the next subinterval over, that would be f7 plus, there we go, so f7 plus 3 times f8 plus 3 times f9 plus f10, and so on. Let's do the ith one here, right? Well, we'll skip over the ith one. So the last one would be f of n minus 2 plus 3 times fn minus 1 plus 3 times fn plus fn plus 1. Okay, let me factor out the 3/8 times h, and let me put same terms together. So I have just 1 times f1 and fn plus 1, so let me put them down here. But then some of these functions values appear 3 times in it. So I can factor out this 3, and they always appear in pairs, right? There's f2 and f3, then f5 and f6, and so then f7, or f8 and f9, and so on. So there's always these pairs of neighboring points. So let me just call them fi plus 1. And look what the I would have to be. Well, it starts at I equal to 2, right? So that means the fi here in the first term, I has to be equal to 2, and that makes the neighbor 3. The next term is f5, so I would have to be 5. And the next one then would be, right, if you look at this one here, f8 and f9, so I would have to be 8. So we start at 2 and then we go by 3s. And we end all the way with the last one here that is at n minus 1. Okay then. And then we have some function values that appear in the sum twice. Let's combine them. So we have 2 times fi. And for the first term, the I is equal to 4. Right? And then the next one here, the I is equal to 7, so we go from 4 to 7. And then the next one is 10, so from 4 to 7 to 10. And where do we end? We end at n minus 2. Okay then. So that gives us the Simpsons 3/8 composite formula, where every function is evaluated just once. Now, this formula is valid only if the subintervals are equally spaced and we have at least, or we have more than 2 subintervals. If we don't have, well, more than 2 subintervals, so 3 and more, if we only have 2 subintervals, well, then we can do Simpsons 1/3. If we only have 1 subinterval, well, then the only thing we can do is the trapezoidal method. And now the other condition is that the way we've derived this formula, the number of subintervals has to be divisible by 3, right? Because we combined always 3 subintervals together. Now, what if the number of subintervals is not divisible by 3, but instead we have like 2 extra? For example, we had 5 subintervals, right? So 3 plus 2 extra. Or 8 subintervals, 6 plus 2 extra. Well, then we're going to use the 1/3 method for the last 2, the extra subintervals. And in MATLAB, how can we figure out whether we have 2 extras? Well, we do the modulus function. So if the mod of n, 3 is equal to 2, then we know we have 2 intervals extra, and we're going to use the 1/3 method for the last two. Now, if the number of subintervals is just one extra, well, in that case, we're going to use the 1/3 method for the last 4 subintervals. Okay, so that's kind of like the 1 extra plus 3. So in MATLAB, you can figure out whether you have 1 extra. That would be the modulus of n, 3 is equal to 1. And finally, if there's only one interval, well, in that case, we have to use the trapezoidal method for that single interval. And in MATLAB, that you check if n is equal to 1. Okay, so let's go back to our example, and let's try this out for Simpsons 3/8 method. This is the data that we have, and we're going to use Simpsons 3/8 method. So we determined before that n is equal to 10. Now that means that if I calculate the modulus, right, the remainder, the modulus of n and 3 is equal to 1, which means that my last 4 subintervals are supposed to be done with Simpsons 1/3 method. So let me mark in here the last 4 subintervals. So that's 1, 2, 3, right, all the way to here. So those would be 4 subintervals. They have to be done with Simpsons 1/3. So I'm going to do here, from here on out, I'm going to do the 1/3 method. And up to here, I'm going to do the 3/8 method. My spacing h we determined before h was equal to 1. So that kind of works out. And all we now have to do is apply Simpsons 3/8 to the first part and Simpsons 1/3 for the last 4 subintervals. So the overall integral, I of f, is approximated as Simpsons 3/8. So 3/8 times 1 times, here is the 3/8 formula. So I have to start out with here the first value. It's the one over here. And the last value is the one over here. So that's the last value. This is the first value. So I have 3/8 times 1 times the first value, 0, plus 3 times the values at 2, 5, and 8. So let me write here the index again. So that's 1, 2, 3, 4, 5, 6, 7. And the n, the number of subintervals, is 6, right? That's divisible by 3. So I have to use here, I have to sum up the values at 2 and 3. So let me mark them, 2 and 3. They have to be summed up. And then the next value would be 5 and 6. 5 and 6, those two, right? Those are these here, 2 and 5. And then the 2 factor here, let me do the coloring here. This guy here, the fi, I start at 4. Okay, then the next one would be 7, but that's equal to, right, I have to stop here at n is equal to 6. So 6 minus 2, I have to stop at 4. So from 4 to 4 is just the 4th point. Okay, now let's substitute these values in. So I have to sum up here with a factor of 3 in front all the green values. So 1 plus 4 plus 16 plus 25. And then plus 2 times all the blue values, that's just the 9. And then I have to add the orange value, the last one. So let's color these here consistently. It's my 36. It's my 0. Those are the green values. So that takes care of my 3/8 method. Okay. And then I have to add the 1/3 method for these last 4 subintervals, right? So they kind of start right here, right? That's where I'm switching over here. So for my 1/3 method, this would be I equal to 1, 2, 3, 4, and 5, right? So for the 1/3 method, I have 5 points, so 4 subintervals, divisible by 2, so the 1/3 method will work. So plus 1/3 times h is still 1 times f1. Well, the f1 is this point here, right, is this guy, the 36. So that's my orange one. So that's 36. That's this guy here. And then I have to add up the 2, 4, and 6. So 2 and 4. Those are these. So plus 4 times 49 plus 81. Then I have plus 2 times this value here. Let's see, let's grab this here. So this guy here, fi. So that would be this one here. I start at 3, right? That's my index 3. So plus 2 times 64. Plus the very last value here, this guy. Just circle this. So plus 100. Okay, so if we type these values into the calculator, we'll find that this is again 333 1/3, which is again the analytically exact answer because, well, if this method is exact for a 3rd order polynomial, or at least the last part for a 2nd order polynomial, that will work and give me the exact answer if what I'm integrating is a quadratic function. Here's the summary for all these Newton-Cotes integration methods. We had the composite rectangle method, the composite midpoint method, the composite trapezoidal method, right? Composite rectangle method used 0th order polynomial, midpoint and trapezoidal used 1st order polynomials. The composite 1/3 Simpsons method uses 2nd order polynomials. And finally, the composite 3/8 Simpsons method used 3rd order polynomials to integrate these exactly. Now, comment on coding. How do we do this coding? Now, you'll see in these formula there's a whole lot of sum symbols, right? So you can either use the MATLAB sum operator, the sum function, or loops with running sums. And you'll also see then in these Simpsons method, we'll have to skip indices, right? We go from 2 to 4 to 6. So what you'll have to do there is the ability to skip entries, either right for a vector index or the loop indices. So as an example here, this sum 2, 4, 6, we can do this as a loop. So we start for I equal to 2, colon, then comes the step size, in this case it's 2, colon, the end index, and the end index is always at the top of the summation symbol here. Or if we want to use the sum function, we just do the sum of f parentheses. We start at 2, colon, step size, 2 in this example, colon, end index n. One more example here, the sum that skips or goes every 3. So that would be as a loop for I equal 4, colon, 3, colon, n minus 2. Right? What you do is always you write as the start index, just the first index that's at the bottom of the sum symbol, and the end index is the last value after the last colon that's written at the top of the sum symbol. And in between you put the step size, and this goes by 3s. And similarly you write this for the sum function if you want to use MATLAB's sum function. Thank you for watching.